So when it's in free fall, we say it accelerates at 9.8. It's acted on only by FG. But if there's air resistance, it's not free fall. It accelerates at something less than 9.8 meters per second squared. It's acted on by force of gravity and drag, air resistance. Okay, so what actually is air resistance? Well, air resistance is essentially air friction. And it's caused by a falling object rubbing against air particles, which is what friction is, right? Friction is an object sliding across the ground amongst particles on the ground, and air resistance is essentially falling objects that are rubbing against air particles they have. So it's the same kind of idea. There he is. We're working on this. Okay. All right, so that's basically what air resistance is. So, what affects air resistance? There are 4 things. Let's start with writing the equation so we can see what each of these things are. So here's the equation for drag. Now, I've got good news. You're not going to have to solve this. Okay? I'm not going to make you solve it. But the equation will be helpful in trying to piece together how things affect it. And the equation is this: 1/2 rho CD A V squared. Okay? Totally good. We got all those things. Easy peasy. Don't worry, I'll tell you what each of the symbols are in a second. Okay. Let's start with cross-sectional area, which is the size of the object. Specifically, it's the flat bottom side of the object. So as the object falls, how much is the area that's in contact with the air? We don't care how long it is. Okay, I don't care what's going on up here because that's not in contact with the air. It's the downside that's in contact with the air. That's what's pushing into the air layer. So that's what I talk about when I say cross-sectional area. That's what I mean. I mean the flat section of an object. So if we're talking about dropping, I don't know, like a stack of paper, which is what we're going to do for the lab, when we're talking about cross-sectional area, I'm talking about this part here. So I'm not talking about the area of the whole object. I'm just talking about the area that's in contact as it falls. Okay? So what's the effect that it has? Basically, larger objects, again, I'm talking about the surface area. So largest, like flattish objects. Larger objects like that are going to fall, have more air resistance. So bigger objects are going to have more drag. Okay, so if you have a giant boulder, it's going to have more air resistance, more drag than a smaller rock. That's the same shape. It's just the size. The cross-sectional area will be different. So larger objects have more drag. Okay, next one. Drag coefficient. What is going on? Okay, drag coefficient. Drag coefficient is the shape of the object. So how aerodynamic it is. Okay, an object that's more aerodynamic, more rounded, allows the air to travel over it easy, that object is going to have a lower drag coefficient. So more more aerodynamic objects have a lower drag coefficient and therefore less drag. So things that are more aerodynamic have a lower coefficient of drag, which means that they have less drag force. So more aerodynamic, better off you are. Again, none of this is surprising. Here's the first one that is surprising. Velocity. How fast you go affects how much drag there is. Now, the reason why is the faster you go, the more air you push through, therefore the more particles you're rubbing against. So the faster you go, you rub on more particles, therefore you have more air friction, therefore you have a higher force of drag. So the faster you go, the more drag there is. And put a nice little healthy star next to that one. The reason is that is the one that usually changes. The other ones generally stay the same. Okay? Generally, like if you're just dropping something off a building, your aerodynamics of the object will be the same. The coefficient, like the size of the object will stay the same, cross-sectional area, and the fluid density, the air density, will generally stay the same. So those three objects will generally stay the same. Therefore, the only thing that will change as it falls is velocity. So the air resistance, the drag will change, and it's usually due to the velocity. Not to say that's the only one. I'll show you an example where that's not the case, where it's not the only thing that matters. But that is the one that's usually the most important. And then the last one here is fluid density. Okay, and that one is this guy here. Greek letter rho. Fluid density is how dense is the air. Obviously, more dense air is going to have more particles, therefore you're going to rub on it more, therefore you're going to have more air resistance. So the more dense the air is, the larger the air resistance is going to be. So the more dense air is, the larger drag will be. Now, you might be saying to yourself, there's something that's not on that list that is very surprising. Anything that's not on that list that you're like, I would have thought it's on the list. Think about what you think. Think about different objects that fall. Which ones you think would have like more or less air resistance? What else do you think might affect it? Yeah, mass. Mass is not on this list. Mass does not affect air resistance. However, it does affect something else. So we're going to come back to mass. But I want to make sure it's clear, mass does not affect air resistance. Okay? Mass does not affect drag. Doesn't affect it. Okay. So before we move on and we talk about terminal velocity, I want to show you an example of this. An example of drag Let me explain why you're not calculating it. The reason you don't calculate drag is it's not a constant value. It changes. And because it changes, you have to use calculus to solve it, which most of you are not ready for. So we are not going to solve for drag just because it's a drag to do. Oh, man. Okay, so let's go ahead and I'm